All right, what do we get started? Welcome back, everybody, to Python for Physics. We're in week 5. Can you believe it? More than halfway there. That's pretty amazing. It's been fun all this time so far, and I'm sure it's going to be fun until the end. So what if we get started the same way that we've been starting classes the last few times? Send us a message. We want to hear from you. We love hearing how you're doing. Tell us where you're coming from. How are things there? Enjoying the class, those types of things we want to hear. So go ahead and do that while I introduce. Oh, sorry, let me edit something. This is an old slide when our colleague Basha Tarsik was working with us. He's too busy with other things, so he's not here. He's not joining us in this class. So let me start with some administrative stuff. As I start usually. If you're new to the class, welcome. If you want to catch up on the things that we have done so far, what you can do is just send an email to this email, pythonforphysics@odu.edu. There's still a few of you that are coming in. If you send an email to this address, you will get an auto reply with all these links, including the page, our web page link, where you can see a lot of information regarding this course and questions that some of you are still asking us. Also, you will get a link to our Slack chat, which is this one. And then this is a place where you can join us and many other participating students to have discussions about your code, the physics. Also, I give a lot of announcements of different activities that are related to REYES, to the program as a whole. So if you join there, it's a much more convenient way for us to have conversations back and forth. I will skip the link because this is where you're seeing this video right now, so you should be there. That's great if you are. If you want to see our recordings from our previous lectures, you can go to this recording link right here. There you will see all the links from the REYES programs, not just Python for Physics, but you'll see all the science content, all the engineering content, the social events content, everything is going to be there, as well as some virtual tours of parts of campus. So in fact, I would encourage you, even if you're just here for Python for Physics, to go take a look here. There's quite a bit of interesting videos worth checking out. So go ahead and take a look. This is all made for you. But if you want to go directly to the Python for Physics archives, you can just go here, as well as our breakout session. We haven't really been taking advantage of our breakout session, so you won't see much there. Most of the content is in the Python for Physics archive. And this is what our page looks like. Go ahead and take a look at this. And the last thing is that if you're a student and you want to have access to a Dropbox folder where you can load your own code, you can upload your own code and share it with us, you should send me an email again to this same link, just with the title line Dropbox access, and I'll give you access to that. I've used this a few times to debug your code and see where mistakes are made. And so it's a useful tool for you guys to showcase what you're doing. This also reminds me of something that we have mentioned at some point, but we haven't really solidified, which is the idea of you doing a project where you can maybe present at the end of the summer. So why don't you do this? Why don't you send us a message on the question box right now, telling us if you would be interested in participating in writing code for some project. Examples could be, given that we're in a pandemic, I thought that it would be fun for you to do some data analysis of the number of cases in your area. Or you can simulate interactions between people and social distancing. So you can do simulations of that. You can also do data analysis of any kind of data out there. You can maybe analyze the CO2 emissions around the world. We can try to consider physics problems that perhaps you can solve. For those of you that are more advanced, that are already familiar with calculus, we can introduce many different projects that are relatively easy once you understand calculus. So if you're interested in doing a project and perhaps we can showcase the results of your code in class in the live session, why don't you send us a message on the question or in the question box or directly to our email saying that you are interested in doing a project, okay? So go ahead and do that, and we would love to hear what you have to say. Also, you can come up with your own project. We don't have to assign it to you. It could be something that you think is cool. Maybe you've created your own simulations using the kinds of packages that Professor Rogers showed. You can do little simulations of animations, I should say, of 1 and 2D systems. So you can do just about anything that you want. So if you have any ideas of if you're interested in an idea of a project, shoot us a message. Okay, so I figured I would start with a little review of what we've seen so far. In fact, I'm not going to do a full review. I'm just going to review what we saw in the last week's set of lectures. And so let me summarize what we've done. And then what I'll do is I'll stop after the review, and I'll wait to see if you have any questions. I see that some of you are still catching up on the previous week's project, so not many of you have already done the analysis that you should be doing for these exercises. And so if you have any questions, you can either send them to the Slack chat or to the, in the stream session, so we can see what you're struggling with and we can try to help you. So the first exercise was just to make plots of the Breit-Wagner distributions. And so you were supposed to pick different values of gamma, 1, 2, 3. So just to remind you, the Breit-Wagner distribution is it mimics, it's a parameterization of the scattering of two particles that couple to some intermediate resonance, and the resonance is an unstable particle that lives for a short time. This particle has a mass m and a decay width of gamma. The decay width is equal to the inverse of the lifetime of the particle, and so this particle lives for a period defined by 1 over gamma, okay? And gamma is related to the width of this. So m is the location of the peak, and then gamma is related to the width of this peak, okay? And this is a function of the energy at which the two particles are scattering off each other, okay? And so this is telling us about the probability of this is telling us about the probability of them interacting, okay? And is a function of the energy at which they're scattering. And so this Breit-Wagner distribution, if you plot it for different values, if you fix m to be 2.5, what I've done in these figures, and you dial gamma to be either 1, 2, and 3, you should reproduce these kinds of plots. So for 1, you should get this red plot. For 2, you should get this blue plot. And then for 3, you should get this green plot, okay? And I'll give you a little bit of insight into what my code for these functions looks like. So it's quite simple. Okay, so that was the first thing you needed to do. And then you had to do some fits. I gave you some data to perform fits of this simulated data. So I wanted to simulate the kinds of what it would be to simulate to fit data that has been obtained from either experimental analysis or from statistical theoretical calculations. And we define a function which was the chi-squared function. Let me see if I have the definition of these. Let me go forward. So we define a function which was chi-squared, which is the goodness of fit. And this function, what it is defined as this difference, the distance from your data, yi, away from the expected value of the data, which is this function f. And f depends on your independent variables, xi, in this case, their energies. But it also depends on some parameters, these c's, okay? So there are some parameters that you input into your functional form, into your function that you expect the data to satisfy. The sigma i's are the errors of your data, and so each yi has an error of sigma I, okay? And so chi-squared is just equal to the sum of the difference from the data to the expected value divided by sigma I all squared. And this is summed over all the possible data points, okay? And so the beauty of this function is that it's defined so that its minimum minimizes the distance from your data to your expected form. And so it's trying to get your expected form as close as possible to the data. And so you can learn the functional form as close as possible that actually describes your data, okay? So you're trying to impose some function, and this function depends on some parameter c, and you want to tune those parameters so that the distance between this y and these functions is as small as possible, okay? And so the function chi-squared is a function of c's. And so you want to pick the values of c such that chi-square is at its minimum, right? Because the minimum distance between the data and your functional form corresponds to the minimum of chi-square. And so we went over that, and I show you some different visualizations for this. And the point, and what I try to explain is that there's many different routines out there in Python, as well as any programming language for minimizing or optimizing functions. And one of these resides, so in Python, one of the packages that has, one of the libraries that has functions for minimizing or optimizing functions is SciPy. And within SciPy, there's another library called Optimize. And within Optimize, there's a function called minimize. Okay? And so this minimize function, it grabs an input function, which I've defined here, chi2 underscore BW, Breit Wagner. And this function depends on a list of parameters. In this case, I defined the list to be n underscore gamma, and the list is just two components, m and gamma, okay? And so what this function minimize is doing is that it's grabbing this two-dimensional list, so this list of 2 points, and is varying these parameters, these two parameters, m and gamma, so that chi-square is at its minimum. And this uses, within the minimize function, you can input your guesses for the optimal values of m and gamma. This is so that you're as close as possible. If you have some good intuition of what these values are, this allows you to be as close as possible to the actual minimum of the chi-square rather than a local minimum. And you remember we saw these plots where I plotted the chi-squared, and you saw that it had a lot of local minimums, but only one true minimum. So I showed you how to work with this minimize function, and then the output that we're after would appear as the output of this function, which I call m underscore gamma. But then you got to take the dot, you got to grab the x element within this gamma. So you grab m gamma. So you do m underscore gamma dot x, and that prints out the true value of the of your parameters. So the parameters that correspond to the minimum function, which is in this case 2.999 and 0.4999. Okay, but here I generated some data using these values of gamma. So m and gamma. So it's pretty close. And so I gave you three examples of fits. The first one was to do a warm-up, which was just to test that you understood how to load data and do a fit. And this was for a constant. And so I gave you some data, which you can find in the Dropbox folder. This link should take you there, or actually this link needs to be updated, but the true link is in the, here, let me just correct this on the fly. It'll take me a second. All right. Look at that. Beautiful. Quick and easy fix. My favorite. Okay. So where were we? We're right here. Okay. So the Dropbox folder is this one right here. And what you will see is, so this is a file inside of the Dropbox folder, I should say. And what you will see is a file that looks like this. You have 3 columns, one corresponding to the independent variable, a second one that corresponds to the dependent, the average value of the dependent variable, and then the third one is the standard deviation. You can load the data following this prescription, and you can check that you're getting outputs of this form. So this checks that you are loading things correctly. You should, if you copy and paste this code, or you write your code that looks just like this, you should be seeing something like this in your screen. Okay, so that's what you should be expecting to see. And what you want to do is fit the data so that it to a constant. Which this means is that what you want to define is a function that is chi-squared of c, where c is just one number, and is defined as this. You sum over all data points, you subtract the value of c, and you divide by the standard deviation, you square everything, and what you want to do is just find the minimum of this function. So you want to find the value of c that corresponds to the minimum of this. And as you can see, you can see what the value is. This is my result, which is 1,000. Okay, you should be getting a number that is consistent with 1,000. So this is just making sure that you're doing this correctly. So hopefully some of you have done this. If you have, let us know. If you haven't, I don't know. I don't know what we can tell you to motivate you. But if you have done it and struggle with this, then let us know. Okay, that's what we're here for. If you need a little pep talk, you should do it. I don't know. I don't know what motivation. All of you guys are very motivated. You're here in the summer, so I'm sure that some of you have tried. And if you haven't tried yet, it's because you're working on the previous one. So I have no doubt that you'll get there. And then the third exercise that I gave you is actual data, under quotation marks, obtained from lattice QCD calculations or simulations, if you want. And what comes out of these simulations are masses of hadrons. If you don't remember what hadrons are states that are bound states of quarks and gluons. So hadrons are the states of the theory of quantum chromodynamics, for short QCD. Okay, and this was one of the questions in the trivia night. So I'm sure some of you that didn't remember what hadrons meant, maybe that you remember after the trivia night. Okay, so what comes out is the pion mass. In this case, I have given you the pion mass, the nucleon mass, and the error on the nucleon mass. And this is data that have been obtained by various different collaborations around the world. So you can imagine that for each one of these points, many months and maybe years of work has gone into obtaining these points. So that's a remarkable achievement. And this, as I tried to emphasize, is actual data. And so what I'm showing you here is a plot of this data. And so you should try to reproduce this plot if you can. Okay, maybe the labelings are a little tricky. Okay, I use some fancy labeling that might be hard for you to make, given the little bit of knowledge that you have so far. So just try to make some labels. It doesn't have to be so fancy. Okay, and so you're saying that nuclear mass is a function of the pion mass. And what we were talking about is that you should try to do a fit where you're assuming a linear. So this data looks pretty linear. It looks like a straight line as a function of this parameter mpi. And so the thing that I was trying to get you to do is do a global fit of this. And this I explain is related to, if you determine what the value is of this parameter is when it crosses, when mpi is equal to 0, I try to argue that this is related to it tells us information about, if you compare this to the value of the nuclear mass from experiments, it gives us information of the contribution of the Higgs to the nucleon. Okay, so it has some significance, this value right here. Okay, if you didn't, so now that I mentioned the Higgs, I should also emphasize that if you didn't see the talk by Max Hansen yesterday regarding CERN, which was a beautiful presentation and giving you a nice introduction into CERN and its history, if you missed it, don't worry, go to the recording session. It should be up either today or tomorrow. It was remarkable, so go check it out. Okay, so you were supposed to do a linear fit, right? And we had a long discussion. Somebody asked, why are we using some functional forms and not others? Can we use something like a quadratic function here? And I made the challenge that, yeah, sure, go ahead and do it. Try to fit a quadratic, or a linear term and a quadratic, or a cubic term, and so forth. You can do that. And what you should see is that the quadratic term relative to a linear term is not that important, right? Because we're seeing that this data looks pretty much like a straight line. And so we're not seeing any curvature in it. There might be a tiny little bit of curvature, but in this region, you're not going to see it by eye. We don't see it by eye, which means that term, the coefficient multiplying the quadratic term, should be pretty close to zero, okay? This, of course, is going to affect the behavior of the function away from the data, right? And this is referred to as an extrapolation, okay? So maybe let me take a second to explain what it means, because this is just generally important. So let me try to connect my iPad. And while I connect my iPad, why don't I let the TAs tell me if there's any questions or comments worth reading?
There's no questions about the review material. However, we do have one about the projects. We're getting quite a bit of excitement about the project idea. And we have a question from Nur Al-Musle from Dubai. They ask, is it possible to upload a list of recommended projects to Dropbox so we can work some or keep the list for future reference?
Sure, yeah, we could do that. Yeah, we can come up. Would somebody maybe mind sending me a message, perhaps on Skype? Somebody in the team reminding me to make a list, and we can start making a repository of lists of ideas.
Sure, I can do that.
Great, thanks, Connor. Anything else?
No, I think you're good to go.
All right, awesome. Okay, so imagine you have some data, right? And let's try to, let me make a little cartoon of what my data looks like. And you see that although it looks like there's a linear trend between all the data, you will see that, so there's a little bit of, wiggle, right? Things are not right on top of each other, right? Things wiggle around, and that's what real data looks like. If you measure things in one point, you might measure them with more precision than others, right? So here, perhaps in this point, I determined things with some level of precision, and here I didn't determine them with as much level of precision. That's okay. That's normal. And so things oscillate a little bit. And so if I try to do a linear fit to this, what I'm trying to impose is a straight line. So, for what I'm trying to do is basically fit, if this is my x and this is my y, I'm saying y is equal to some constant plus b of x, right? And I'm varying these parameters so that I get as close as possible to the data as possible. And so for some values of a and b, maybe it looks like this line that I just drew, but then eventually, if I do enough of a good job, I'll get something that looks like this. I'll get some line that crosses all the data, okay? And if I then try to make a prediction, sorry. Let's see if I can come back. Can you see my screen now?
Yep.
All right, good. So if I then try to make a prediction about what the value of this function y is, somewhere in between my data, then here it would be, this would be defined as it would be defined as an interpolation. So I'm grabbing information of data in this region, and I'm trying to interpolate I'm trying to obtain a value in between, and this is known as an interpolation. I'm trying to obtain a value of my function inside of the region that I've constrained that function, okay? So that's an interpolation. And so the reason why this matters is that if I introduce a function that is not like this, but rather is something like ya plus b of x plus c of x squared, right? You see that my data does not seem to have much curvature. And so I will probably get something that is pretty close to the blue line, okay, in between. But if the coefficient is not exactly equal to 0, right, but instead is some value that is pretty close to 0, but not exactly equal to 0, then away from this region, it might start to matter. And certainly away from this region, when x gets bigger, it's going to start mattering, right? And so depending on the relative values of b and c, this can then lead to a dramatic difference in my predicted values at different points of this region. And so when I'm, sorry.
There's not always an easy answer.
That's true, Siri. Thanks. All right, Siri is telling us that there's not always an easy answer, which I think was about to be my punchline anyway, so she just got ahead of me. So if I then try to make a prediction away from the region where I've determined my data, so let's say in this region, so let me use a different color. What color? Orangey? Why not? So if I try to predict then my function, I try to make a prediction of the values of this function away from where I've constrained with data. This is known as an extrapolation. Extrapolation. And extrapolating is always much harder. Okay? And in science, this is only really possible if we really know what the actual, this is only rigorously possible if I know what the actual functional form is that describes my data. If I know the true functional form of that data, not just some functional form that I guessed, okay? And I need to know that that functional form is either exact or very, very good in the region that I'm extrapolating. So I have to have some mathematical argument that justifies that. And that's always hard to do. And so this is, why predicting things like the stock market, weather patterns, is just very hard, because you don't know you don't have data about the future. All you have is data about the present and the past, and you don't always have the right functional form that is the right mathematical form that is going to behave not just in the past and present, but also the future. That's just hard to do. Okay. So my point of all this was, if you do a linear fit and a quadratic fit, you should see that your results will differ a little bit in the extrapolate, but the punchline in this case is not going to be that. The punchline is not going to change, basically, for this case, because I've done that fit too. All right, so hopefully that explains a little bit of what this exercise was supposed to be. And then the last one was, I gave you some data for a Breit-Wagner distribution. So here's some data that I generated in a text file over here. And what you were supposed to do, this is supposed to mimic an experiment, a particle experiment. And what you were supposed to do is do a global fit using your Breit-Wagner distribution, tune your mass and gamma parameters so that you fit this data, and this is what I got. Okay, so you should see something like this. You should be able to reproduce this plot. Okay, and these are the equations that we covered. Basically, the only two equations that we introduced in the whole previous chapter. Okay. Do you have any questions, any comments, anything that you want to ask before we move on? And this is really for the TAs to tell me if you guys have any questions or comments. Or do they have questions or comments for me?
No, I think you're good to keep on going.
Okay, sounds good. All right, if there's no questions, why don't we just dive in? So we're going to change topics completely, completely today. And what I figured we would introduce is magnets, spin, which is a property of particles, and the interaction between particles that have spin. And also we're going to introduce concepts of symmetry and degeneracies. Okay? And so first, we're going to dive a little bit into the quantum mechanical world of magnets. But first, why don't we start by just understanding magnets, or just refreshing our memory of how magnets works classically. So here, what I'm showing you is a bar magnet, just a simple bar magnet with a north end, with a north pole and a south pole. And what you're seeing are images of the patterns that iron fillings take in the presence of bar magnets. And this is illustrating what this image is trying to illustrate. I mean, it's just showing almost exactly, is that there's a field, there's some action, that there's a field that is generated by this magnet that is felt by these iron fillings that forces them to align themselves in these forms. And this is the magnetic field, okay? And many of you are familiar with magnetic fields and how they interact with compasses, right? So the compasses that you use for guiding yourself in where the North Pole lies, or where the northern direction lies, is essentially a little iron filling that is interacting with the magnetic field that is generated by the Earth. And so some things that are worth remembering is that if you grab two bar magnets, they will interact, so they feel each other. So if you grab two bar magnets and you align them, the north end to the south end, they're going to attract each other. While if you grab the opposite, or the like ends of the poles, so of the North Pole and the North Pole one magnet and the North Pole of the other magnet, they're going to want to repel each other. And this is also true for the south end of the south pole of the magnet of one, if you put it close to the south pole of the end of the magnet of the other. So unlike poles attract, like poles repel. Okay, so they interact with each other, they feel each other's presence, and so that's suggesting that there's a force that is attracting these two and then is repelling these two. Okay, and I already mentioned that the Earth itself generates a magnetic field, which is what compasses align themselves, and that the north end. So basically, you have a little compass which has a north end and a south end, and the north end towards the north, which is, if you think about this, the fact that the north end of one bar magnet always is attracted towards the south end of the other magnet. This is telling you that the north end of the compass is pointing to the geographical north, but is pointing to the magnetic south pole of the Earth, which is closely aligned to the geographical north end. And so essentially the Earth's magnetic field can be thought of as being generated by a bar magnet that is with the south end of it being to the north pole, the north geographical pole. And you can make this picture a little more concrete with the iron fillings. If you then, instead of using just iron fillings, you can also introduce the compasses, which then interact with, that start to align themselves in the direction that the magnetic field of this bar magnet is pointing. So in this case, you see that the north end is pointing away, which is consistent with the shape that the iron filling is taking. Here, the north end is pointing away. In this case, the north end is pointing towards the left, also suggest, also consistent with this picture. And so this is all to say that if you think of the magnetic field as to be consistent, to be pointing along the direction that each one of these compasses is pointing, or the ion fillings are pointing, is consistent. So there's some magnetic field that looks kind of like has this form that is being emitted from each one of these bar magnets. Okay. Then the other important observation is that there's a connection between electricity and magnetism, and this is really driven home in the second course of any introductory physics course. And you can see this being manifested in the fact that if I grab a loop of current and I have a loop of current that, so I have just a loop of a wire, and I drive a current through it, what you end up seeing is that if I put now iron fillings, you see that the iron fillings start to arrange themselves in a similar type picture as over here. And what you can deduce from this picture is that the little loop, current carrying loop, acts effectively like a bar magnet. Okay, so it has some direction, some preferred direction for the magnetic field to point. So it has a magnitude in a direction. Okay, so it's saying that the magnetic field is pointing inside of it, is pointing towards the right with some amount of magnitude, and this magnitude is tied to the amount of current that we're driving through the loop. So if you have some wire and there's no current running through it, you won't see this effect. But if you start running current higher and higher, you will start seeing this kind of effect. Okay, and you can see this. This is reproduced in all sorts of different configurations of current. So if you drive a wire, if you have a wire with a current going up, let's say, then you will see that there's the iron fillings start to align themselves around in these circular shapes, suggesting that there's a magnetic field that is wrapping around these wires. This already showed you. If you then have not just one loop, you have many loops that are connected one with the other. What you see is that this picture gets a little stronger, so it starts to look even more like a bar magnet. Okay, and so this is a way for you to generate a magnetic field just using current. So if you have a current and you wrap it around in a circle like this, then you would generate a magnetic field. And so this is the actual pictures of currents and iron fillings, but here you have the mathematical. You have depictions of the magnetic fields just from the mathematical expressions that you can derive in a second semester of physics. And so you see that the magnetic field does indeed look like a bar magnet, and it becomes even more so once you put more and more wires stacked up next to each other. Okay, and so how do we then, given now that loops, little current carrying loops, look just like bar magnet, and we know that bar magnets can attract and repel each other, then this already tells us that if I submerge a current carrying loop near a bar magnet, this is then going to experience a force. And so it turns out that the details of the direction and the magnitude is, it's we don't need to go into. But basically, if you have a current carrying loop, so you have a loop that has a current inside of it and it's just wrapping around, and I bring this near a magnet, then it will indeed either repel or attract, depending on the direction of where the current is going, and also in the direction that the magnet itself is pointing. Okay, but this does end up looking like a little bar magnet in this case, looking like so in this case, which wasn't going. So in this case, it has it looks like a bar magnet going towards the left, with the north end pointing towards the left. And so these two repel. But in this case, if I align them this way, they're going to each other. Okay. Okay. So what this does is that it allows us to construct. So this picture was led to the first classical pictures of how to understand how magnets can be described microscopically. And so one microscopic picture is that we can think of the particles. So material is just made out of electrons, protons, and neutrons. Okay, that's it. Just different combinations of this. And so let me just think about the electrons inside to make my life easier. And so the electron, here's my little cartoon picture of the electron. What we know now, at least at this point, is that we don't see the electron as an actual size, but imagine that it had a size, okay? We know that it does have magnetic moment, so it does have properties that look like it acts like a magnet, okay? That we know. And so the question is, how can we describe the fact that it has some magnetic field, that it generates a magnetic field? Well, if we think of it as a classical sphere, and we try to think of it as, if it's a classical sphere with charge, if it were to be rotating and spinning about some axis, what it would do is that it would generate a current, right? Because it has charge, it has some distribution of charge inside of the sphere, and if it starts to wrap around itself, it would start to generate a current. And current is nothing more than charge that is traveling over time. Okay, so it's just some charge that is traveling, and so effectively, this picture is consistent with a little loop that has current flow, that has charge flowing through it. And so as a result, it looks like a tiny little magnet. Okay, and so it has a tiny little magnet. And so a lot of times this magnetic field, the source of the magnetic field in these particles is described as spin, because it looks like a particle that is spinning. Now, at least at this point, the quantum mechanical picture of this is not that there's an actual particle that's spinning, but instead that there's an intrinsic property of particles that is called spin, that is a source of the magnetic field. Okay, but it's just something that some particles have. Essentially, every single particle in the Standard Model, except the Higgs, has a non-zero spin. Okay. The fact that the Higgs doesn't have a spin would at least to suggest to many people that it's kind of weird, and maybe there's something special about the Higgs. Okay, so every single particle out there has an intrinsic property that's called spin, and it comes from the name comes from this kind of cartoonish picture that is a little charged particle, and then it's moving around some axis. Okay, and so how do we then think about unmagnetized material? So most of the materials that we interact with each day doesn't have it doesn't have it doesn't generate a magnetic field, and that's because all these particles that are inside of the material that carry spin are aligned in random directions, such that the sum of the total spin, meaning the spin which is associated with this current, this little loops of currents, the average of them averages to zero. So they don't carry any spin. Magnetized materials are those where this spin, the average of them does not average to zero, but they're aligned to have some effective direction or some preferred direction. In this case, is pointing in this direction. Okay, and so that's effectively how we can think about materials with non-zero magnetic field. Okay, or non-zero, yeah, with magnetized materials that generate a non-zero magnetic field. Okay, so that's my introduction into magnets. spin, magnetized materials. Yeah. So hopefully that was, if you haven't seen this stuff before, hopefully this makes a little bit of sense. If it doesn't make sense right away, that's okay. Hopefully it starts making sense with time. And also you have access to the slides so you can see them with more patience, with time when you have it. And so what we're going to do here is try to model how spins inside of material works. And to do this, we're going to use the simplest model possible. And the most famous model of this, which is relatively simple but also remarkably powerful, is referred to as the Ising model. And this is named after Ernst Ising, who worked on this So he solved this this problem of how to think about systems with spin in the simplest scenario possible, which is essentially the one that we're going to consider here. Okay. And so in the Ising model, spins are fixed. So we're going to think about atoms as fixed, and they can have some spin that could either be up or down. That's it. We're not going to allow them to rotate. Nothing complicated, just very simple, okay? And so they can either point up, in which case we give them a value of +1, or they can point down, in which case we're going to give them a value of -1, okay? And so they can, the spins that are close to each other, they can either align with each other or they can anti-align with each other, okay? So depending on the material and for certain alignments of the spins, it might be favorable or disfavorable for the spins to either align or anti-align, okay? And the way that this manifests itself is in the energy that is stored in the system, or equivalently in the energy that is required to put the system in a given configuration, okay? And so what we're going to do is to mimic this system is that we're going to consider n number of spins. N can be any number. It has to be an integer number because we can only have integer number of spins or of spins in a ring. So we're going to put them in a ring. So here's a little cartoon of what I'm thinking about. So we're going to put little spins in a ring, okay? And we're going to enumerate the spins from 1 to n. Okay, and in this example, n is 6, but in other examples, we're going to pick it to be different values. Okay, and we're going to number them 1, 2, 3, 4, 5, 6, and so forth. Okay, so we're going to label the corresponding spin, the value of the spin for each one of these as SI. So the ith one is going to have a value of SI. So for example, here 1 has a value of S1, which is equal to 1 because it's pointing up in this little picture, okay? And I've also color-coded them for your convenience. In this one, S2 is pointing down, so I'm going to give it a -1, okay? And so this defines what I mean by spin and what is the mathematical representation of the spin. So it's either going to be 1 for up or -1 for down. Simple, okay? And so in this example, we have n is equal to 6, and we've used the following. We have the following values of the spin: 1, -1, -1, 1, 1, -1. Right? 1, -1, -1, 1, 1, -1. Makes sense, right? So that just sets up what do we mean by spin and what value we're going to give them. Okay. Now, what we're going to do is that this allows us to model the energy of a system with n spins using a fairly general expression, which is the following. So in this, I'm using here E is the energy of the system, okay? And it depends on 3 parameters, A, B, and C. Easy enough, right? And so what A, B, and C are the values of these parameters that appears here. So these are just constants that are some generic property of the system. In general, I could maybe describe just about any system using, a function like this, system spins, I should say, and some values A, B, and C. And so, what are the things that are multiplying A, B, and C? So let's try to break it down. So first, let me, I have some symbols. You see that I'm summing I from 1 to n here, and I have Si and Si plus 1. In this case, I have Si multiplied times Si plus 2. And in this one, I'm just summing over Si's, okay? So let's walk bit by bit this expression, see what it means. Okay, so I have Si times Si plus 1. This means that one must multiply the value of the spins that are nearest to each other together. For this to make sense, we need to define what do we do with with the term that is n plus 1, that is meaning if I have to sum this all the way for I to equals to n, in which case I'll have n over here, and then I'll have n plus 1, right? And so what we're going to do is impose periodic boundary conditions. And this is consistent with this picture. You see, if here n is equal to 6, right? When I go to 1, 2, 3, 4, 5, 6, and this is n, and I want to add n, I want to add 1 to n, I'm back to 1. Okay? So that's referred to as periodic boundary conditions. And then for n plus 2, that's equal to 2. So this is what we mean by periodic boundary conditions. So once I go around the circle, I'm back to the origin of the system. And so you can imagine this kind of picture. So for example, here are the numbers for the examples shown in this figure. Okay, so if I have I equals 1, then I plus 1 is equal to 2, I plus 2 is equal to 3, and then if Si in this case is equal to 1, Si plus 1 is equal to negative 1, right? That's going to be this guy. And then the product of Si plus times Si plus 1 is just a product of these two numbers, which is equal to negative 1. And then this one is just going to be the product of 1 times negative 1, which is also equal to negative 1. Okay? And so if you want to check your understanding of what these parameters mean, just check out this table. Okay? All right. So to define where physically these expressions are coming from, let's think about each one of the terms separately. So in the first one, the first term in the energy expression over here, so the first one, let me call that one EA, okay? And this is just the multiplication of this coefficient A times the sum of the products of the spin with the closest nearby spin, okay? And what this tells us is that each spin experiences the field that is generated by the closest neighbor, right? Each one of the spins is a little magnet, and it creates a little magnetic field, okay? And the strength, and because of that, they're either going to be attracted to each other, they're going to be repelled with each other, and so it's going to translate into some energy in the system, okay? And the strength with which this contributes to the energy is going to depend on the value of A, and of course on the product of the two spins. Okay. The next term is essentially the same story, but now in this case, so here you have a little cartoon, right? I showed you in the first case you have a little cartoon where you have a system with a spin down, and then nearby it is, so you're considering the spin of the first one, which is up, and then nearby it is the one with a spin down, and so this experiences a force due to the magnetic field of this guy, and so that's going to affect the energy of the system. Okay, but that also could be the case for not the nearest neighbor, but the one that is 2 steps away. Okay, so in this case, this one, okay? So same thing, you're going to have an interaction between this spin and the one that is 2 steps away, and the coefficient that parameterizes this interaction is this parameter b, okay? And then the last one that we're going to have is just one, is this coefficient, is this term which depends on this coefficient c, which is the sum, it's just multiplying the sum of all the spins. And this just accounts for the possibility that there might be some external field, right? I could submerge this ring inside of, well, if it's on the Earth, it's going to feel the magnetic field of the Earth, right? But I can also submerge it inside of a bigger magnetic field. In this case, I'm going to assume is uniform, meaning it's going to be the same acting in all, it's going to act the same on all the spins. And how this acts is going to be parameterized by this coefficient c. Okay? And that's basically it. That explains intuitively which, where each one of these terms is coming from. Okay, so let me maybe take a second, take a sip of water, and see if the TAs have any comments or questions for me before I go on.
Yeah, there are some questions here. We have a question from Nur Al-Musle from Dubai. They ask, is spin an intrinsic property, something similar to mass? As far as I know, mass and charge are also intrinsic properties. Mass itself comes from interaction with the Higgs field. And are there any models that is trying to predict where does spin come from?
Okay, that's a great question. Does anybody else want to take it? I could take it if you guys want.
Yeah, I think so.
Okay. Yes, spin is an intrinsic property as far as we know. Meaning it's one of those properties that particles have, and at this point, essentially, we can't really explain. They just are what they are. Mass is one of them. It does come from the Higgs field, from the interaction with the Higgs field. But effectively in the world, effectively you can think of it as the masses as also as just being intrinsic. And so, yes, charge is another one. There's other, so those are just properties that particles have that are just intrinsic to them. Are there theories that are trying to explain where perhaps spin comes from? I'm sure of it. I can't think of any on top of my head. Let me get back to you about that. That's a good question. But I can't think of anything on top of my head right now. Okay. Is there any other question?
Yeah, we have a few other questions, kind of with a common thread between them. I feel that there's a little bit of confusion between the distinction of a magnetic field and an electric field and how one gives rise to the other. Would you mind going over that briefly again?
Yeah, sure. So we're not talking about electric fields here at all. So electric fields and magnetic fields are tied together. So if you have an electric field, so actually, if you give me a hot second, what I can do is just pull out, I just taught this class last semester. So do you have any other questions you can get to without my help for a second? And I can just pull out some slides that I think would be useful. Is that a no?
Yeah, no, I just briefly looked over them again. I'm not seeing much else.
Okay, sounds good. Give me a hot second. Okay. So I should have. I think these are the ones that I want. Oh no. 29 maybe. Good. Okay. So at the end of your first year in physics, what you would have reached is, hopefully, is Maxwell's equations. So Maxwell's equations are a summary of 4 equations that were pieced together at the end of Maxwell. James Maxwell, shown here, he's one of the most significant scientists of the last couple of centuries. And what he noticed is that, so let me walk you through Maxwell's equations, which not all of them were presented by him, and they carry different names. So the first one is Gauss's law. Gauss's law, I'm not going to walk through the mathematical symbols because I'm not going to assume that you know calculus. But here, this is the electric field, and what is shown on the right-hand side is the charge density. And so what this tells you is that electric fields are generated by electric charges, by charges. And so if a particle has a charge, it will create an electric field. And what a field is basically an abstraction of how we can think about forces between different objects. Just like how you're being pulled down right now towards the Earth and you're feeling an attraction to the Earth, you can think of the attraction being between you and the Earth. Or what you can think about is that the Earth is creating a gravitational field. And you're submerged in that gravitational field. And what you're feeling is the pull down because you're inside of this field. Okay? So it's an abstraction, but it's remarkably powerful. And so the electric field, what you can think about the interaction between 2 different charges is that, let me show you let me do a little multimedia response to this question. So if you have 2 charges, let's say they're both positive, okay? What you know is that, if they're both positive, this charge right here is going to experience a force this way, okay? But what you can also think about is that this particle, this particle right here emits an electric field in all directions. And I'm not going to get into why it has to be this way. But then, so this is an electric field. This is what E is, okay? And if I put then this charge, let me call this one to have a charge Q. You can define the field such that the force that this charge experiences is equal to its charge times the electric field. If you're not familiar with this little symbol on top, and perhaps I haven't done the best depiction of it, this is a symbol for a vector. A vector is nothing more than a quantity that has a magnitude, but also a direction. So in this way, in this case, it is pointing towards the right, okay? And so the force, I can define it between the 2 particles, or I can define the force to be experienced by this particle or it can be a consequence of this particle interacting with the field that is being generated by this other particle. Okay? So that's my mini introduction to fields. Okay? And this is also relevant in like I said, gravity, and in fact, every single particle that we describe now, we use something called field theory, where we think about particles as excitations in some field. Okay, so fields are remarkably important. And so electric fields can be generated from electric charges, just like I just showed. There's a second law, which is this one, which I'm not going to define this mathematical object. It tells us that there's no magnetic charges. So charges, magnets don't have a what is called a magnetic. There's no magnetic monopoles like there are charges for there are electric charges. There's no magnetic charges. If you find one, you will most definitely get a Nobel Prize. Okay, I'll say that much. The second equation is Faraday's law, which gives you a relationship between the electric field and the magnetic field. And so here in particular, you're seeing this is a variation of the magnetic field as a function of time. Okay, and this is a variation of the magnetic field as a function of space. Okay, and so the punchline is that if you have you can have electric fields if a magnetic field is changing as a function of time. Okay, that's what this equation tells you. The last equation, which was the one that Maxwell completed, is known as the Ampere's-Maxwell equation, which tells you that you can generate magnetic fields from either moving charges. So you can have a charge that is moving, and it creates a magnetic field. And this is related to currents, right? So if you have a current, there's charges that are moving. So currents are defined as charges that are just moving. Okay, so you can have magnetic fields from charges that are moving, or with from electric fields that are varying with time. Okay, and so this 4 equations describes that electric and magnetic fields are different manifestations of some underlying field, electromagnetic fields. Okay, so you can tie them together into some set of fields that are related to each other via these equations. And so this was the reason why this is so significant, is because you had these different phenomena, electrical phenomena, magnetic phenomena, that seemed to be unrelated, but that really were unified into one underlying force, which is the electromagnetic force. They're tied together. And so this was the great insight of Maxwell. And so then this led to these ideas that physics must be unified in some scale, that different forces are really manifested. They're different manifestations of just one underlying theory. And that's what the Standard Model does for 3 of the 4 forces that we see in nature, and ideas of grand unification, which is what Einstein, was really interested in, and many others have tried to follow along his footsteps. We're trying to unify all the forces that we see into one set of field equations. Okay, that was a long ramble for a much simpler question. Does that address the question a little bit?
Yeah, I think you actually managed to address a few different questions at once with that, I think. So, good.
Awesome. Cool. So, but yeah, if you want to understand this stuff, you really have to take a second semester in physics, which I strongly encourage everybody, because when electricity and magnetism is just really beautiful, especially when you tie them together into Maxwell's equations. Just you see these different things that you thought were totally unrelated, and then just get tied up together into Maxwell's equations, which you can even write in much simpler forms than the ones that I wrote down in that page. Okay, so I think maybe we should continue, unless there's any other questions at this point.
You can push forward.
Okay. So the next thing that before I start introducing some problems, I figured I would take this opportunity to introduce a little bit of symmetries, the role of symmetries in physics. And so what we're going to do is determine the energy using the Ising model for different configurations of spins. Okay, so we're going to grab spins and put in different configurations, and so we're going to play around with that. But before we do that, I thought it would be nice to introduce some new concepts. And the first one is symmetries. The second one is going to be degeneracies. And so symmetries is arguably the most powerful, one of the most powerful concepts in physics. It's certainly one of the most powerful. It's arguably maybe the most powerful. I don't know. That's maybe too much. And it's guided from some major insights in physics in the last century. And one of the major insights, which is that drives a lot of modern physics, is related to Noether's theorem. And if you don't know Emmy Noether, I'm not going to have a chance to introduce Noether's theorem, but just so you know, so she's a famous German mathematician and physicist, and she was described by many famous physicists, perhaps the most famous of all, Einstein, as one of the most important women in history of mathematics. And I think she's simply put as one of the most important mathematical physicists of the 20th century. And her theorem explains the connections between symmetries and conservation laws, which are essential for how we think about, for some pieces of the standard model of particle physics. So this is, her theorem is one of the first things that you learn about in a class of quantum field theory, which is the mathematical framework that we use to describe particle physics. And so if you haven't heard about her, I would recommend you to learn about her. And in fact, this week on Friday, we're going to have a talk here in REYES by Felipe Ortega Gama, who is a student of William and Mary, who works with me in different research projects. And he's going to tell us about the role that symmetry takes in physics and how it can be used in physics. So if you haven't learned about symmetries, what I'm going to give you is a tiny little introduction, and he's going to do a much better introduction. So I would encourage you to go check that out on Friday. And so intuitively, the way you can think about symmetries is by considering objects that are symmetric under reflection and those that are not, okay? And so here's an object that I just drew. And what you can see is that about some axis, so in this axis, this is symmetric under the reflection along that axis, okay? So it's symmetric about this. And in contrast, you can see an object here that is clearly not symmetric about a reflection along this axis. And so equivalently, one way to, that you can think about symmetries is to think about it in an active way, which is to ask yourself what actions or transformations leave the system that I'm considering invariant, or in other words, unchanged, okay? So what kind of operations or transformations or actions I can apply on the system so that it remains unchanged, okay? And so in this case, I have a reflection symmetry, or equivalently, a rotation about the center axis, okay? So it's symmetric about the same axis as I said, and so if I rotate it around that axis or I flip it, it's going to be left unchanged. Okay, so what we can start to ask ourselves is, what kind of symmetries does our system of spins have? So I think I wanted to say systems of spins. Systems of spins. And so in general, the expression that I wrote down is kind of complicated. So to simplify things first, let's turn off the external field, okay? Let's assume that these particles are not submerged in some external field, which amounts to me stating that this coefficient, the third coefficient in that expression, equal to 0. And so in this case, the expression that I consider simplifies a little bit, okay? So if I said C equals to 0, then I just have these two terms, okay? And so I could just now, again, consider some arbitrary arrangement of spins. And so I can start to ask myself, how what kind of rotations I can make on the system that are distinct. So how many distinct rotations can I have? And which ones of these leave the system invariant? So here what I'm thinking about is rotating the system where I essentially make a mirror, I just take the system and I just grab its mirror image, okay? So I'm replacing these two together, these two, and these two, okay? And so what we see is that, so alternatively, I can also make reflections where I flip everything by the plane. So I can do rotations where I just rotate about this axis, which means that I flip these two, or I can just flip all the spins to be equal to the opposite of the spin. So I grab all the up spins and make them all down spins, and all the down spins and make them up spins. And so in this case, is this the symmetry rule percent? Okay, so the point is that each one of these actions leave the energy of my system invariant, because this only cares about the relative spin that I have between the nearest neighbors or the next nearest neighbors, okay? So in this case, you can think about the interaction that this has with this guy is unchanged when I flip them over, because they're still relatively opposite in spin, right? While this one with this one is relatively opposite in spin, and now in this case, that's gonna be translated to this other neighbor, to this next to nearest neighbor. And so the energy of the system remains unchanged. And the same is true in this case. If I flip all the spins, the energy of my system remains unchanged. And so it seems like these types of rotations leave the system invariant, or more specifically, it leaves the energy of the system to be the same. And so the next question to ask, because we're going to play around with different possible configurations of the spins, is to ask ourselves, how many possible ways can I align the spins? And so if you take a second, I'm sure you can figure this out. You want to give it a shot? Anybody out there? All right. I'm going to assume that you got the right answer. So good job. Well done. So if you have n spins, the possible number of spin configurations that you can have is equal to 2 to the n. Why is that? Well, if you think about it, what do I want to do? Let me put. So if you think about it, right? Let me just think about 2 spins, right? So here's 2 spins, and here's my ring. Boop, boop. It's kind of silly to put a ring like that because they're just 2, right? And so what are the possibilities that I have? I have the possibility that I have, for each one of them, I have to pick 2 possibilities, right? And so I can make them both up, right? But then I can imagine fixing the left one and then varying the other one to be down, right? And then I've exhausted all the possibilities. So this is my 1 possibility. This is a 2 possibility. Now I've exhausted all the possibilities where the first spin is pointing up. And so the next one, I have to point the spin down for the first one. And the other one, again, could be up. Or it could be, again, this one has to be down. And then the only other possibility is for us to be down. Okay. And so what you can think about is that for each spin, if I have n spins, for each spin, I will have 2 possibilities. And so I will have 2 times 2 for each one of the spins, all the way to 2, where this is 1, 2, all the way to n. And so this is also known as 2 to the n. Okay. So that makes sense. And just to make it that much more explicit, here I consider a case where n is equal to 3, and that tells me that there should be 2 to 3, meaning 8 different configurations. Okay, and each configuration, I'm going to refer to it as a state. So it's a state of the system. And so I can have where first I just aligned these, I drew them so that I fix the first spin to be up, and then I put a comma, and then I think about the direction of the second spin, and then I put a comma, and then followed by the spin of the third one, okay? And so these are just different spin configurations, all of them first being up, then I can flip the last one, then that exhausts all the possibilities where I have the first 2 up, and so then I have to flip the second one, so that's what I do. Again, I can flip the last one, and then in the second row, I just essentially copy this first line, but now I flip the first one. Okay, and that exhausts all possibilities, and you can count them, right? You have 4 on top, 4 on the bottom, that equals to 8. Okay. Okay, so hopefully that makes sense. And so the next concept that we have to introduce is the idea of a ground state versus an excited state. And the ground state is basically the configuration of the system that we're considering. That so in general, nature, what it wants to do if it's left alone is to minimize the energy budget of a system. Okay. And so they want to, particles eventually want to arrange themselves in such a way that is most energetically favorable. And so qualitative, what we're trying to do is trying to find the minimum energy of the ground state corresponds to the minimum energy that I can give a particular system, okay? So here's a qualitative example, just, a useful one to keep in mind, where you have a ball in the presence of gravity. It wants to eventually the ball always wants to roll down the hill where the potential energy is at its minimum, right? And so if you lift a ball alone, the potential energy is going to always try to drag it to its minimum energy, right? Of course, if this started above here and there's no friction, this ball is going to continue going up, okay? But this is just qualitatively how you can think about the system. And so ground states is just going to refer to the minimum energy of the system, and we're going to try to figure out what is the ground state of different systems defined by this expression of the Ising model. And finally, the fact that your system can have some symmetries, it implies that different spin configurations can have the same energy. And so this is an important concept that is introduced in quantum mechanics that tells us that is known as degeneracy. And I point you to a Wikipedia page on degenerate energy levels. And so if you have a system that has that is invariant under some symmetry, so I can relate 2 different states via some transformation that leaves the system symmetric, then those 2 states have to be degenerate, okay? And so if so here's an example of 2 systems, 2 states that are absolutely degenerate, always, they have the same energies, regardless of the values of A, B, and C. And so the question that you can ask yourself is, what, if this is the case, then there has to be some transformation that relates these 2. There has to be some relationship between these 2. And think about it for a little second. You look at these figures, you can try to convince yourself that I can create this state by just simply rotating this other state. So I just rotate it by 1. I just move all the spins over by 1. I can create this state. And so these 2 states are related by rotation. in this case of I don't know how many degrees, and there's nothing in this in the energy of the system, the expression of the energy of the system that we're considering, that depends on the rotation, that depends on the let's say the alignment of this relative to some angular rotation. So these two have to have the same energy. Okay. And so here's another exercise. Here's an example where I can now ask you, are these two states going to have the same energy, meaning are they degenerate for all the values of A, B, and C? Or in other words, are there any restrictions on A, B, and C, remembering that the energy of the expression for the energy of systems with spin that we're considering is given below. A is the term that is telling me about the relationship between nearest neighbors. B is telling me about the next to nearest neighbors. And then C is telling me about the interactions between the spin and some external field. Maybe the thing you want to ask yourself first is, how are these two states related? It looks like I can generate from this state, I can generate this one by just turning all the blue dots to red and all the red dots to blue, right? Which amounts to grabbing all the spins, flipping them. So all the downs go to up and all the up spins go to down, right? And so it doesn't affect the nearest neighbors interactions because what matters is the relative spin between the two, right? So if I have a relative spin like this and I flip it, that doesn't change anything, right? I just do this, essentially is what I wanted to do. So the product of 1 times minus 1 is equal to the product of 1 or minus 1 times 1. So that's unchanged. Same thing for the next to nearest neighbors, right? If I do this, the same as this. But it does affect the last term, right? Because the last term does depend on the overall spin of the system. So you can just sum the spin of the system. In this case, I have 1 plus 1 plus 1 plus 1 minus 1 minus 1. So that's equal to 2, right? In this case, I have 1 plus 1 minus 1 minus 1 minus 1 minus 1. That's equal to minus 2. And so here I would be multiplying C times 2. In this case, I would be multiplying C times minus 2. And so these two states are only degenerate if C is equal to 0. Makes sense, right? Good. Okay, so let's consider another example. Here's an example. Takes a little second. So the question again is the same one. The question isn't changed. I've just given you two different spin systems. And I've asked you if these two are always degenerate irrespective of the values of A and B and C. Okay, so I'll give you a second to think about this. Okay, so again, you can look at the figures and it takes a second and you can see that these are related by, I can either relate them by making a mirror image around this axis, or I can just flip them all the spins. So that tells me that it's going to be degenerate independent of A and B, but we have to be careful about C, right? Is there a specific value of C? And here, we can just do the same exercise we just did, right? We can just sum up the spins, right? So we have 1 minus 1, 0, good. Plus 1 plus 1 minus 1 minus 1, 0. So the total spin of this system is 0. Since this is a mirror image about the plane of the system of this one, that tells me that the spin of this one has to be 0 as well. I can also do the counting, of course. And so that tells me that this coefficient, the number that's multiplying C, is 0. So I can pick C, the coefficient, to be any value I want, and these two states are always going to be degenerate. Okay. All right. So degeneracy just tells me that two different states that may seem different have exactly the same energy. Okay. So these are some relatively simple examples for understanding how degeneracy works, of course. And that tells you that if two states, what you can think about is that if two states are exactly degenerate, there has to be some symmetry relating them. And to give you an example in particle physics, nuclear physics, the proton and the neutron are remarkably are remarkably close to being degenerate. So actually, let me look up the masses, because I know the difference between the two, and I know the neutron is heavier. But I forget them. Okay. So here's a symmetry that is almost a symmetry. So the proton is made out of 3 quarks: the up quark, 2 up quarks, and 2 down quarks. The neutron is made out of 2 down quarks and 1 up quark. Then the neutron mass is equal to 39 MeV. So in some units of energy, it's equal to that. And then the proton, what is the proton? The mass of the proton is equal to 938 MeV. So first off, if you forget that the neutron is heavier than the proton, you can think back at the slides that I presented a couple of weeks ago, that I showed that the neutron decays into, so the neutron decays to a proton plus an electron plus an antineutrino. And so for this decay to be possible, the electron has a non-zero mass, right? The neutrino, it turns out, I mean, it has a tiny little mass, but it's non-zero, but it's tiny. But the proton has a non-zero mass, obviously. And so for this decay to be possible, the mass of the neutron has to be bigger than the mass of the proton. Otherwise, if you go to a frame where the neutron is just at rest, we know that the energy has to be conserved in this reaction, right? And so whatever the mass of the neutron has, the energy of the total energy of the neutron is just stored in its mass. And so whatever this is, it's going to have to be equal to the mass of the energy emitted by the proton, the electron, and the antineutrino. And the minimum energy that the proton can have is equal to its mass. And so this is always going to be equal to the proton mass. Okay? But the thing that is astonishing is not that the neutron is heavier than the proton, but it's how close this number right here is compared to this number. right? That's remarkable. So close. Okay? And so this is telling us that there seems to be a symmetry that if and the other thing that you should notice, right, is that I can relate the proton and the neutron by just replacing all the down quarks with up quarks and vice versa. So if I flip, if I think about all the up quarks, and if I think about up quarks and down quarks as two different configurations in some abstract space, and I can perform some rotation or some transformation that grabs all the up quarks to down quarks and all the down quarks to up quarks, you can see that under that transformation, that takes all the neutrons, it takes a neutron to the proton, and the proton to the neutron. And the fact that these two are so closely degenerate to each other suggests that this transformation seems to be almost a symmetry of the standard model of particle physics that we see, or our universe, essentially. And we see this everywhere. So this transformation seems to persist. We see that all the states that if I create some state, let's say, so here's a state, if I flip all the up and down quarks together, and so I create something that looks like this is a up and an anti-down. If I flip it to be a down and an anti-up, these two states are exactly degenerate with each other, or they're close. In this case, they're exactly degenerate. But in general, if I perform any transformation, I create some state that is composed, let's say, let me grab a less trivial example. Something that is like up, up, strange, and I flip this to be down, down, strange. These two states are very closely degenerate with each other. And this is a symmetry that is known as isospin symmetry. The spin part is suggestive that it looks like spin in some abstract space. So yes, symmetries, degeneracies so symmetries and degeneracies are closely tied to each other, and symmetries are remarkably important in how we understand physics in general and in particle physics. Okay, so when I gave you some set of exercises of things that you can start playing with to get you playing in with different spin configurations and trying to obtain what the energy is for different spin configurations. So the first thing that you can do is, the first thing you should do, right, is write a function that holds for n spins. So it's independent of the number of spins that are aligned in a loop that gives me back the energy of the system given some values of A, B, and C. Okay? And I've done this in a somewhat clever way, so you're free to do this however you want. But first, I define a vector, a function that rotates a vector. And so what this code does is that if you give it an array, it's going to rotate that array to the left by 1. Okay? And so what I do is that first the input is called vec0. So let me try to put this next to my And the reason why I'm showing you this part first is because if you understand this part, then the second part is just very easy. It just becomes quite easy. And so let me try to explain what I do. The first part that you see is that I've used the function length, which gives you the length of an array. So let's what do we call a simple array, which is this, which gives me a range, gives me a list of integers starting from 0 all the way to the value that I've given it -1. Okay, so I've given it 10, so it goes from 0 all the way to 10 minus 1, in other words, 9. Okay, and so a couple of things. If you're not familiar with arrays, they're really powerful, they're really great, and so you should make use of them as much as possible. And so the list, if I grab some array and I do open brackets and I give some number in between, what it's going to give me is the element, is that corresponding element in the array. Okay, so x0 is going to give me the 0th element, which is the first one. And so in this case, it's giving me 0, right? Here, this thing, I've made it a little bit confusing, right? Because it's going to look like this is a function that is just returning back the number. So why don't we make x a little more interesting? Let me do this plus, I don't know, 12. Okay, so now I've just shifted all these numbers by 12. So 0 goes to 12, 13, yada, 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 right? Okay. And so, again, let me just test x of, grab the 0 component of x, and that gives me back 12. The first component, the 1 component gives me 13, and so forth. If I try to grab it 10th element, it's going to complain, right? Because I'm starting to count, even though the length of this is 10. Remember, I'm counting from 0, right? And so the largest element that it's going to consider is 9, which is the last one, and this is going to be 21. Okay, so first, the length of x I can obtain by using len and then open parentheses and x. Okay, and so you see here that I've defined something that is equal to, let me just define vex0 to be equal to x. Okay, let's print out vex0. Good. Same thing as x. Okay, good. And so here I've defined n to be the length of vex0. And so now n takes on that value, which was 10. Good. Then I define a temporary set of array that is empty. And I'm going to call that temp. And then I use a numpy function 0, and I make it of length n. And so what this gives me is an array of length n, in this case is 10, which is just a bunch of zeros. And so you print it out, and you get an array of zeros of length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. And I can check this by just printing out temp, the length of temp. Good. Okay, so there's a little bit of now gibberish here, and this might be a little bit confusing. So let me first look at what the right-hand side is doing. So let me do vex0. Let me print out vex0 one more time, okay? And then here, what I'm doing is that I'm printing out the elements that go from 1 to the length of the vector 0. So it starts from the first component all the way to the end. I think I could also use this. Nope, I could not use that. Does this work? Nope. Oh, I thought I could use -1.
Sorry, I didn't get that. Could you restate the question?
I'm good, Siri. Thanks. Okay, so I guess I gotta use this. I thought you could use -1, but obviously it doesn't. It doesn't work because it takes you to the second to last one. Does this work? This does work. Good. Okay, got it. Remembering my syntax. So this also works. So if you do 1 and then colon, it prints out starting from 1 everything that goes all the way to the end. Okay, so this works too. What I have there also works. So both of these works. Both of these syntax give you the same thing. So that's a good thing. The important thing, right, is that it starts from the second element, right, which is labeled by 1, all the way to the end. Okay? And what I'm going to do is that let's just stick to what I had before. What I'm going to do is that I'm going to put these into temp, starting from 0 and going to the last one, -1. Okay? So let's do this. And the thing that you can do, sometimes if you ever screw this up, what you can do is that you can print out first the length of vec0. Just copy and paste because I'm getting lazy. So you can always just print out this, right? And you want to shove this into something called temp, and you're going to start it from length of 0, from the 0th element to the n-1 element, right? And so you want to, whatever this is, you want to put into here. You need to make sure that they're the same size, right? And so this is, of course, just a bunch of zeros, but I'm going to set these zeros equal to this over here. And so now we can print out temp. In fact, let me just print out. You see, I've now replaced what I was calling before, what I called over here. I replaced it with the information obtained from vec0, right? So let me just print this out. And now you see it went from zeros to 13, 14, all the way to 21. In fact, let me just print out the whole temp. And you see, I've defined now, I've replaced all the zeros, almost all of them, except the last one, which is still a 0. And so what I've done is I've grabbed vec0, I've grabbed this information over here, and I've moved it over by 1 to this over here, okay? But I'm not done, right? I still got to replace the last one, right? And so, again, I can use different things. So I can use, this should work. Yeah, this works, good. Okay, so temp -1, or I can use temp n-1. This should also work, good. Okay, either one of these work. Vec0, so what I want to do is grab this last component, which is 0, and I want to replace it with the first component of vec0. Ta-da! You see? So I've just shifted everything by 1, and then the first component, I can't take it to the left, right? I got to move it all the way over, right? And that's what it means to be in periodic boundary conditions, right? If I shove somebody over here, then that person is going to go all the way to the end of the line. Makes sense? Okay, so this allows me to just do a little rotation or a shift by 1, okay? And so this is my function, and it see that although I defined this function, I played around with a function with this example for 10 slots. You see that here I'm not making reference to any size slots. Right? I didn't say 10 or 9 or anything, right? This is just generic for any vector of length n. Okay, so it's pretty general. And then here I'm going to define the output of this function. And I'm going to do this in just a few lines. First, this grabs a set of spin configurations. So I've generated some spin configurations, okay? And that's what this ST is. ST is just an input, which is an array of spins. And it's just ones or negative ones. That's all it is. And so the first thing that I defined is that I grab the spins and I rotate them over by 1 by calling the function above, the rotate underscore vec function. And I call that STP1. I think P1 refers to +1. I can't remember. Just one rotation, right? And just shift them all over by 1. Yeah, it's +1 because I'm grabbing the plus. The ith component is being replaced by the I +1. And then to get, you see this thing depends on SI +1, right? It depends on SI plus 1, as well as SI plus 2. And so to get the SI plus 2 vector, all I have to do is just grab the plus 1 and rotate it again. And so that's what I do. I just rotate it one more time. And so I have ST plus 1, ST plus 2. Good. And so now the expression for obtaining this energy is quite simple. I just break it up into 3 different terms. The first one is a nearest neighbor interaction, and it's just A times the product of sum of ST times the product of ST plus 1. Okay, if you're not familiar with products of arrays, just play with it. So let's do again, let's just grab this function A range. Okay, so now replace X with just the A range of 10. Okay, if I just multiply X times X, what am I gonna get? Well, I'm just gonna get each component and grab it squared. So 0 times 0 is equal to 0. 1, 1. 2 times 2, 4. 3 times 3, 9, and so forth and so forth. Okay, so this function, this product of string of arrays, just multiplies element by element. Okay, then the other thing that I use is sum. Okay, which is for any array. So in this case, for X, if I do the sum of X, it's just going to sum all the components together. Okay, and so it's going to give me 45, right? So why is that 45? It's simple. 1 plus 9 is 10, 2 plus 8 is 10. So I have 20, 40, and then I'm left with the 5. So that's 45. Easy, right? If I then square these, then it's going to be just the sum of this squared. And so that's 285, because it has to be. I don't know. And so that's what this sum function is. And so dA is just equal to A times the product of the sum of ST times ST plus 1, right? And that's giving me this term. And you see, I could have done this also with a for loop, but this actually is much faster. So in Python, these routines for summing and products of arrays are much faster than for loops. And then same thing with the B term. I just grab ST multiply times ST plus 2. And sum it, and then lastly, the C term is just C times the sum of all the STs, okay? Which is also, the sum of ST is also gonna be the sum of the ST plus 1 as well as the ST plus 2, because it's just a rotation, so the sum is invariant under rotations. Okay, so I think maybe we need to cut it off here, and so why don't you go ahead, write code for this, and then we can walk through the other exercises that I have lined up once you have this ready, okay? So I think we have time for a few questions, if there's any.
Well, yeah, we have just a more general question about the presentations from Joseph A. on Slack. He asked, hello, I have a question. How long are the previous streams going to be available until the REYES program ends, or will they always be accessible?
Oh yeah, they're always going to be accessible. So if you, yeah, so we're trying to make this material available for everybody indefinitely. We know that some of you have become increasingly busy over the summer, and then many of you couldn't join us in the live sessions in the past, and you're just catching up now. And really our goal in REYES and here at ODU, I mean, we work a lot on outreach and trying to encourage people to gain the tools to get involved in the sciences. And so what our goal is to make as much scientific content available for you to learn at your own pace, and for you to be able to hear about different research outlines and perhaps get to meet people that could be future mentors of yours. So the material is always going to be available in this page, in the REYES page. If you go there, you'll go to recordings. These are the videos that I mentioned. So we have some videos associated with giving you summaries of what each week content is like. And these are virtual tours of different parts of campus, as well as different videos summarizing different fields in the university. One that I would encourage you to go check out is the ODU Nuclear and Physics, Particle Physics Research Group. But also, we're always going to have the material available here. So for Python for Physics in here. Any other questions out there?
Not that I see.
Okay, sounds good. All right, everybody. So why don't we cut it off there? So next there's going to be a panel on people of color in STEM. So as many of the programs that many of the panels that we've been hosting are related to diversity and trying to show you paths. We know that you're reaching us from different parts of the world with different cultural, ethnic backgrounds, and so we want to show you that how different paths that you can take to get involved in the sciences. And I think hearing from people that have passed through similar experiences and that you may be going through may be of quite a bit of service to you, and also to understand how our paths, I think, is always enriching, even for those that perhaps have a more straight path into sciences, to hear from other experiences that some of us have gone through to get us to where we are. And so I would encourage everybody, regardless of where you are from and how you identify, to go check out this panel. I think it would be quite enriching. So go ahead and do that. Go take a look at that. And then tomorrow, we're going to have a couple activities, including I'm going to be hosting a panel completely in Spanish with faculty in Spanish from the College of Science and Engineering. Also, Giovanna Gennard, our Assistant Vice President for Strategic Communication and Marketing, will be present. And we're going to have representatives from the Embassy of Mexico here in the United States. So if you're interested in doing careers in science in the States, and you're more fluent in Spanish, or you're in Latin America or anywhere in the world, and you want to hear about possibilities of career paths here, come join us. I think it will be quite a bit of fun. So I think if there's nothing else, maybe we'll leave it there. And if I don't see you in tomorrow's panel because you don't speak Spanish, you could always also join and practice your Spanish. But if you don't see you tomorrow, I'll see you again Thursday.